Hello everyone, this is the second class for probability chapter 2. So today we're gonna see the axioms of the probability at first, and then we're gonna see conditional probability. So after doing these two steps today, on this Thursday, we will gonna cover these other two topics. So then we can finalize chapter 2 in this week. So even though the slides are or lectures are a little bit shorter than offline lectures, it is absolutely fine to make up our schedule because in general in online lectures I'm not doing some interactive stuffs. It's almost impossible. So during the offline classes I'm asking some questions, I'm repeat some examples in order to make sure that you guys are understanding fully. But in this case, I just make one directional lecture. That's why it is relatively shorter than offline lectures. But you don't need to worry about that too much because we are on time, we are on schedule correctly. Furthermore, if required, I'm gonna do some makeup classes. I'm gonna organize some makeup classes in order to explain these online stuffs again during offlines. So we can have Q&A sessions at the time. So you don't need to worry about too much. In addition to that, if you have any questions, you can email me or you can make a comment in the YouTube website in the video lecture. You can make a comments about that. So in the comment, you can write down your questions if you have, okay? So first of all, I would like to let you know that what is the probability? Probability are the numbers assigned to event. So we have S, which is called sample space. So in a sample space, we have everything. So suppose that we are tossing dice. In dice, we have 6 different options. So 1, 2, 3, 4, 5, 6. So this is everything what we can get by tossing the dice. That's why this is everything. That's why we are saying that this is a sample space. This is a sample space here. But among this given sample space, we can define event. Suppose that our desired event is even numbers. So that is called A, event A. This is event. So in event A, we define that this is even number. Then we are saying that this is 2, 4, and 6. So eventually, among given these 6 different options, we have interest in these three numbers, 2, 4, and 6. That's why this is 1 over 2. So this is our event. So this is the event. Okay. E means random experiment. So if we have controlled experience, then we cannot define the probability. We have to get the probability in a random situations. That's why we have random event here. So in this probability theory, we have several axioms. So axiom means that we can use these steps without any proving procedure because this is obvious. They are obvious statements. That's why you have to remember this one. So in this case, for the action first, we can say that probability of A is larger than or equal to 0. So every single probability should be larger than or equal to 0. This is obvious. So that's why we can use this one without any proving procedure. So the probability of the sample space itself should be 1 because given sample space we are selecting everything. That's why the probability should be 1. We can use this one without proof as well. So suppose that we have no overlap between the set of A or event of A and the set or event of B. So in this sample space S, we have A and we have B. We have no overlap because there's nothing in this intersection. So in between an A and B, we have no intersection. Then if you want to get the probability of the union of A and B, then this is our result. And then this is also same with the probability A plus probability B. So this is probability A, this is probability B. So by doing the addition of these two probability, then we can see that they are same to each other. Okay. So axiom 4 is a generalization of the axiom 3. So in axiom 3, we are defining this result in 2 event case. However, in axiom 4, we are defining this property in n number of events. So then in n number of events, and any kinds of the pairs of A and B, A sub I and A sub J, if there is no intersection at all, just like this one, and then we can say that the union of the event, the probability of the union of the event equals to the probability of the events summation. Okay, so because we have no overlap between them, we have no overlap among the given events. That's why this is also obvious in this axiom 4. So based on these given axioms, we will gonna define some properties or corollaries of probability theory. So here we are starting with corollary 1. So in this sample space S, we have A, we have the others. So probability A plus probability A complement should be probability of sample space. Okay? So probability of sample space should be 1. That's why probability of A complement should be 1 minus probability of A. So we can easily solve this one. But in this case, the reason why we can do this one is that there is no intersection between A and A complementary. That's why we can use this theory, and then we can make this one because this is same with S. That's why this is by axiom 3, and then this is 1. That's why this is by axiom 2. So we can use the axioms for doing the proving of given statement or corollary. So every single probability should be less than equals to 1. If this is an empty set, then should be 0. If this is a sample space itself, and it should be 1. So actually events are between empty set and sample space. That's why it should be less than equal to 1. Okay. Also we can say that PA plus PA complement should be 1 because this is the probability of the sample space. And then we can say that this is larger than equal to 0 by the axiom 1. Axiom 1 says that every single event should be positive or equals to 0. That's why this is larger than equal to 0. This goes to right hand side. Then PA should be larger than equal to less than equal to 1. That's why this is true by this axiom 1. For the next, this is obvious that the probability of an empty set should be 0. That's why this is obvious. That's why we don't need probability. Corollary 4 is exactly same with axiom 4, right? So if we have a lot of events and then there is no overlap among this given event, that's called pairwise mutual exclusive. So in this case, we can do the union at first for the given events, and then we can take the probability on top of the result. That should be same with the case where we are taking the probability of every single event at first, and then we can do the summation. Okay. So this is directly obtained by this axiom 4. However, you can do the proving by using mathematical induction. So you can do it by yourself if you want. Otherwise, you can just say that this can be obtained by this axiom 4 directly. Okay. And then we have another corollary, but this is maybe you guys studied about this one during your high school ages, first grade of high school. So this is A union B, and then you are taking the probability of the A at first, and then you are taking the probability of the B. Then you can see that this area is considered 2 times. That's why you have to do the substitution, this space 1 time. Then we can get this one. So we can easily do this proving procedure by drawing this Venn diagram. However, you can also say that so A union B entire set is the summation of A union B complement, this one, and then A intersection B complementary. This is B intersection A complementary. That's why this space. This is A intersection B. That's why this space. Then this is A union B. And A means this one. That's why this one plus this one. That's why you have this one. B means this space and this space. That's why you have this one and you have this one. So when you are doing the summation of this one, then you can see that you have 2A intersection B, whereas this has only 1 intersection A intersection B. That's why you have to do the substitution of this 1A intersection with B. Okay, that's why you can get this result. Then in general case, suppose that we have 3 events. Before starting, let me erase everything. Okay. Before starting, you have event A, you have event B, you have event C. So you want to get A union B union C. So then you have to take the probability A plus probability B plus probability C at first. And then you are computing this one two times. You are computing this one two times. You are computing this one two times. But in this case, this is three times. This is two times, two times, two times. Then you have to do the substitution PA union intersection B, PB intersection C, P, C intersection A. Then this one, we have nothing here because we are doing substitution three times. That's why this becomes 0. That's why we have to do the one more addition of A intersection B intersection C. That's why the sign is plus, sign becomes plus minus plus. That's why we have this one, okay? When we are doing the generalization of this equation. So corollary 6 also can be proved by mathematical induction if you want, but you can just remember this result only, okay? So next, the other case is that A is the subset of the B. Then the probability A is less than the probability of B. That's true by this example, but we can make this kind of solution procedure. So in this case, P of B can be defined as P of A plus A intersection B intersection A complementary. So B intersection A complementary. Okay. And of course, since we have this one, so this is larger than equal to 0. That's why B is the EP equals to P of A plus something which is larger than equal to 0. That's why P of B is larger than equals to P of A. That's it. Okay, this is by axiom 1 because every single event's probability should be larger than equals to 0. That's why by this axiom 1, we can easily prove that this is true. Okay. As I told you before, we can define the sample space, okay? But sample space can be finite or infinite. So for example, dice case, dice tossing, we have 6 different cases. 1, 2, 3, 4, 5, 6. For the other case, infinite case, we can just say that, okay, x is larger than 0, less than 100. So in that case, we can pick any kinds of values between them. That does not need to be integer, does not need to be any kinds of number. We have no restrictions about that. Okay, that's why we can make these kinds of continuous domain, or we can define these kinds of discrete domain. Okay, then let me start with the discrete domain. Okay, suppose that we have sample space S, we have n different event or something like that. So suppose that we are doing the dice tossing. That's why we have 1, 2, 3, 4, 5, 6. Okay, the probability of the 1, probability of 2, probability of 3, probability of 4, probability of the 5, probability of the 6. If the dice is fair or there's no control actions, there is no engineering or manipulation on top of the dice, then we can say that the probability of each number should be evenly equals. That's why this becomes 1 over 6. That's why this is true. Okay. So this is the example of a finite case. So we are doing the toss. We are doing coin tossing. So in this case, once we are doing the coin tossing, we're gonna see head or we're gonna see tail. So we have two different cases, head or tail. Okay, and we are tossing a coin 3 times. That's why when we are doing the coin tossing, then when we are doing once evaluation, when you are doing single evaluation, then we have 2 different type of the result, head and tail. And when we are doing the 3 times operation, then we have 2 to the 3 different cases. That's why we have 8 different cases. And here we have 8 different cases. This is head, head, head for these 3 times iterations. And we have head, head, tail, head, and so forth. Then our event is that we need something which has 2 head. So here we have 2 head, 2 head, 2 head. Okay, that's why this is our interesting reason. And then we can divide just like that because they are mutually exclusive. When we have this one, we cannot have this one. When you have this one, we cannot have this one. That's why they are mutually exclusive. So in this case, as I told you before, since we have 8 different cases, this is 1 over 8, 1 over 8, 1 over 8, entirely this is 3 over 8. Okay. So now we are doing the toss of coin 3 times again. Now we have interest on the number of head. So we may not have the head. That's why 0 can be possible result. And then we have only 1 head. We can have only 2 heads. We can have 3 heads, and that's it. We cannot have 4 heads because we did 3 times operations. So this is our sample space, as you can see here. And then now we have interest where we have 2 heads. That's why only this one. So among this given 4, we have interest on this only 1 case. That's why this is our result. So now we have, so in this example, we are interested in finite case, and then in this case we have interest in infinite case. So in this case we will define the reason of these variables. So here we will pick 2 numbers at random between 0 and 1. So x, this is x, this is y. This is 2 random values. X can be 0, x can be between 0 and 1, y can be between 0 and 1. That's why this reason is our interest. That's why this is our sample space. Okay. Also, we can define just like that, x and y, 2 random numbers, and x should be between 0 and 1. This is also should be between 0 and 1. So now, our interest in event A is that x is larger than 0.5. We have no restriction on y. So here, this is for A. This is for A. We have no restriction on top of y. But we, in x should be larger than equals to 0. That's why this is our interest. So in entire set, the half of the reason is our interest. That's why the probability is 1 over 2. Okay. In case B, y should be larger than 0.5. It means that we have no restriction in terms of the x, but y should be larger than 0.5, 1 over 2. That's why this is our interest. And then we can say that the half of the reason, half of the sample space is of our interest. That's why this is 1 over 2 as well. In C, x is larger than y. That's why this is our interest. In this case, you can obviously see that this is half of the given sample space. That's why the probability is also 1 over 2. So this is the axioms of the probability. It's very easy, and we can see some properties in probability and something like that. Now we're gonna see the conditional probability, which is very important in many applications. For example, AI, decision theory, or something like that, or communication theory. So suppose that we have 2 events, A and B. Then we have to find conditional probability of A given that B has occurred. It means that we have to get the B at first. And then when B is occurred, we will gonna see A. So in this is we can make the description just like that. Suppose that B happens at first. If B is not happening, if we are in the B complementary, then those are not our interest. Okay, we will not see that anymore. We will see only B space. This is our interest. So you can easily imagine that this is our new sample space. Okay. So among this given space, our interest is A. That's why here our A is here. This space is not in B. That's why these are not our interest. Only this space is our interest. That's why we can say that P of B is our given condition. Okay, this is our new sample space. And then inside there, we have to find A. That's why this is A intersection B. That's why we have A intersection B. But in this case, our basic assumption is that we should be able to have B for sure. If B is empty set, then we cannot say this kinds of theory. That's why the basic assumption is that B is positive. In the same way, suppose that A is given, it means that A is our new sample space. A is our new sample space. We're going to see inside here. So we're going to see only A. And then here's B. And then once A is given, then we have to find the B. That's why within here, we have to find B. That's why we have probability B at A at first, and then we have to take the intersection of A and B. That's why this one. Okay. In this case, as I told you before, our Bayesian assumption is that probability of A is positive. A should be existing, and then we can say right after that. Okay. So in this case, based on this result from here, we can multiply P of B both case because P of B is positive. That is possible. Then we can eliminate this one. Then A intersection B can be denoted by this one. In the same way, by doing the multiplication of P of A in both sides here, and we can say that this will be eliminated, and then we can say that P intersection A, P of B intersection A equals to this one, okay, when P of A is positive. So now we have one example. Suppose that we have one on here, and we have 2 black balls and 3 white balls. Okay, and then we will select 2 balls, 1 time and 2 time, and without replacement. Okay, and then find the probability that both balls are black. So for the first stage, when I pick one, that can be black or white. So if that is black in the first trial, then we'll go this way. In the first trial, if it is white, then we'll go this way. Okay. So in this case, when you take the black, the probability will be 2 over 5. That's why we have 2 over 5. When we take the white, then the probability will be 3 over 5. Okay. So in this case, when we are here, B was taken for the first trial. That's why black was taken for the first trial. That's why we only have 1 black. We have 3 white. So in this case, for the second trial, we take the black again. So in this case, the probability will be 1 over 4 because we have only 1 black ball among this given 4. That's why we're gonna have 1 over 4. But in this case, in the second trial, this probability is for the case where we take the white. So in this case, we have 3 among given 4. That's why we have 3 over 4 here. So in this case, so white was taken. So here we have 2 black balls and 2 white balls. And then when you take the black ball in the second trial, we're going to take the 2 over 4. That's why we have this one. If we are taking the white ball in the second trial, then we'll take this 2 over 4. That's why we have 2 over 4. So then, now in this case, both balls are black. So black and black. So we're going to take this probability and this probability. That's why our result will be 5 over 2 multiplication 4 over 1. So this result will be 1 over 10. Okay. We can do the calculation just like that. Or we can say that in the first trial, it should be black. In the second trial, it should be black. And then we can take the intersection. Okay, that is possible. As we studied before, probability is given at first. And then when this is satisfied, then we'll take the probability of this one. They are same to each other. So this means that for the first trial, black was taken. So this means that suppose that for the first trial, black was taken. In this case, in the second trial, the second trial should be black as well. So they are same to each other. So this probability is 2 over 5, as you can see here. And this case, this is the case. Because B1 is given, that's why we have to look at only this case. So this is 1 over 4, this is 3 over 4. That's why we only have 1 over 4. Okay? That's why by doing this one, by having this one, we have to do the multiplication with this one and this one. That's why we have this result. Okay. So we have another example. So we have a transceiver, TX, transmitter, and we have RX, receiver. And we have 0 and 1 transmission. And in this case, the probability of transmission of 0 will be 1 over P, 1 minus P. The transmission of 1 signal probability will be P. And in this case, when 0 was received, it can exactly decode that this is 0, or by having noise in this wireless channel, 0 can be misunderstood by 1. So in this case, this probability is 1 minus epsilon. The error decision will be epsilon. Decision error with probability epsilon. Okay. So once this one received 1, and then the RX can say that this is 0 by mistake decision error with probability epsilon, or this can exactly say that this is 1, correctly say that this is 1 with the probability of 1 minus epsilon. Okay, so here we can draw a tree just like that. In the initial phase, if 0 is transmitted, then the probability is 1 minus p by this one. And then if it transmit 1, then the probability will be p by having this one, okay? And then in the Rx side, this is Tx side, transmitter, this is receiver. This received 1, and then this is correctly decoded that this is this received this 0 was transmitted at first, and receivers received the 0, and then it correctly decoded that it is 0. Then we can say that we correctly decoded the signal. That's why we have 1 minus epsilon. Even though Rx received 0, if it says that there is 1, then we have error. That's why we have epsilon here. On the other hand, in this side, transmitter sent number 1. And if we have a mistake over there, the receiver misunderstood that there is 0, then we have error epsilon. And when receiver, on the other hand, when receiver received 0, and then it can misunderstood it as 1, then this transmitted 1, and then it decoded it as 1 correctly, then we have 1 minus epsilon, okay? So in this case, when we have this way, then we have 1 minus p, 1 minus epsilon. That's why we have this result. When we have this path, we have 1 minus p and epsilon. When we have this path, we have a p multiplication epsilon. When we have this path, we have a p multiplication 1 minus epsilon, okay? And this can be denoted by as left-hand side. So here, in the transmitter side, it sends 0. In receiver, it understood that there is 0 correctly. So since they have correct transmission, that's why we have 1 minus epsilon. Since they sent 0, we have 1 minus p. 0 was sent, that's why we have 1 minus p. But 0 was misunderstood to 1, that's why we have epsilon, because we have error, we have decision error. So here, we sent 1, and then it was misunderstood as 0. That's why 1 probability is p, and misunderstanding probability is epsilon. That's why we are saying that this is p epsilon. So lastly, transmitter sent 1, and then receiver get that signal correctly as 1. That's why this is the transmission probability of 1, and then this is the probability of the correct decision. That's why we can define just like this one as well. And in this case, we're gonna see the case of total probability law. So we have one sample space. So one sample space is divided by multiple segments, is B. And then we have no overlap at all, or in addition to that, we have no intersection. We have no empty space. We have no intersection as well as we have no empty space. Then we are saying that they are mutually exclusive, okay? So in this case, the union of every single segmentation equals to S. That's why the probability of A can be denoted as A intersection S. And then the S can be denoted by this one. By doing the distribution law in this set theory, in set theory, we can develop this one just like that. This can be go to this one, go to this one, this go to this one, this goes to this one. That's why we have this result, okay? Then, as I told you before, these are all mutually exclusive. Then by using corollary 4, we can say that the union of every single event probability can be developed as follows. It means that we take the probability of every single component at first, and then we can do the addition eventually. So this is talking about that. That's why P of A can be denoted by this one, the probability of individual intersections. And then we know this equation, okay? We saw this one in our conditional probability introduction section, maybe here, right? We saw this one. We saw that here. So that's why every single intersection can be denoted by this one. So this becomes this, this becomes this, this becomes this, okay? And this is called total probability law, okay? So we will use this one eventually, okay? So we had this result on this example, two black balls and 3 white balls, okay? So we have to do selection 2 times. We have to take 2 balls without replacement, okay? And then we have to take the probability where the second ball is white. We don't need to worry about the first ball. So in this case, first one is black, and second one is white. So this is our interest. So first one is white, second one is also white. So this is our interest. Okay. So we have to take the probability of this one. So then, so here, for the first trial, the case for the first trial, we have to take the case where the ball is black. So first is black, first is black. Second can be black or white. Okay. First trial should be white. So this is white, this is white. Second one, we don't need to care, black or white. Okay. Now our interest is our second trial. Second ball is white. Okay. This is our interest. So in this case, we have to say that second should be white. Second should be white. So we have two different cases, this one and this one. This one means that for the first, our given condition is that the first one should be black. The second one is white. So first is black and then second is white. For this case, this is case 1, this is case 2. For the case 1, this is case 2. So this is case 2. First is white, second is also white. So this case, okay? So then we are saying that we have to look at only this one for the first case. We have to look at only this one for this second case. Because this, as I told you before, when we explain here, I told you that this is new sample space. That's why we don't need to worry about this one. We have to focus on this one only. That's why here we have to focus on inside here. So this one, this is 3/4. This one, 2/4. Okay? So now, by the total probability law, which means that we want to take the case where the second trial is white. Then we have to take both cases. So B sub 1 happens at first. In this given condition, we have to take this one. So in this case, in this figure, this should happen at first. And then we have to take this one. That's why this becomes 4/2. This becomes 4/3 by doing this one. Okay? In this case, this happened at first, and then this happens. Okay? So this one is 3/5. This one is 1/2. That's why we can get this result. So we can solve this problem with the total probability law as well. So lastly, so we have Bayes rules here. Bayes rules is very important in decision theory, statistical decision theory, classification, machine learning, deep learning, statistics based, and then in communication theories. That's why this is very important. So if you have some time in the end of this class, in this semester, I would like to give you some supplementary materials. Those are talking about statistical decision theory based on the Bayesian rules. That's why this is very important. But in the textbook, we have just a quick introduction. When we want to calculate this one, this is conditional probability. That's why we have to put the probability of A at first, and then we have union, just like that, as we studied in here. Okay, we emulate this one or this one. Okay, this is much more similar. And then by doing conditional probability law, and then we convert this one as this one. By doing total probability law, we convert this one as this one, because probability 1 is the summation of the all conditional probability of each segmentation. Okay, that's why this can be generated. So one thing you have to remember from this Bayesian rule is that in this case A was given, and then we are calculating the B sub j. But now B sub j is given, and then we have to calculate the A. They becomes opposite by doing these Bayesian rules applications. That's why eventually we will gonna see some examples how Bayesian rules can be used for the statistical inference later, not this time. At this time, we just remember that there exists Bayesian rule which can be denoted by this slide. So this is the end of class today. So for the next this Thursday, we'll cover these two topics. So thank you very much today, and then we're gonna see on Thursday again.